Okay, so we are back in action now. We have another example here, which is very similar to the one that we just solved together. So I'm going to leave this one for you to solve on your own. It's very clearly stated, it's elaborated on in the text. So please solve it on your own and make sure that you agree with my answer. Um, and let's move on to another topic here. I did mention previously that if we're solving for R from our fundamental discounted cash flow equation, it might be difficult and we might have to iterate. Okay, so let's talk about why. Let's consider just a simple situation like this, where we have our present value, PV tot, is equal to 10, which is comprised of two tranches, a payment of 6 divided by 1 plus our interest rate raised to the 1 year, so that payment's going to come in a year, plus a payment of 8 divided by 1 plus our interest rate to the 2 years, so that's going to be a payment in 2 years. So the 8 will be discounted back 2 years, the 6 will be discounted back 1 year, okay? And we don't know R, so how do we solve for R? Well, as usual, we use the magic of algebra and we multiply both sides by 1 plus R squared in this case and rearrange terms a little bit, and we get something that again looks like more of the dread high school massacre algebra. And this is clearly finding the roots of a quadratic equation. And as we all remember from high school, or maybe earlier for some of you, there are in general two roots. Which one is the right one? Sometimes we have a double root, sometimes we have complex number roots. So that makes things difficult. Also, what if we didn't have integer times for our cash flows here? Then we would have non-integer exponents here, and we'd be solving for the roots of what we call a real equation, and there is no quadratic formula for that. Also, what if we had a project with 3 years worth of payments? So let's say we had plus 3 divided by 1 plus r cubed, then we'd apply the magic of algebra and we'd have to be finding the roots of a polynomial of order 3. So you can see where I'm going with this. It, in general, gets hard to solve the equation, which may be the roots of a real equation, which is very difficult to do, needs to be done numerically, or a polynomial of order n, which is going to have n roots, and we don't know a priori which is the right one corresponding to the interest rate. Okay, so that's going to be an issue. We'll come back to this more later, but I just want to give you a heads up about that sometimes finding R is difficult. Okay, in a lot of multiple cash flow projects, the future cash flows are all equal. So in other words, we could say F1 for cash flow 1 is equal to F2 for cash flow 2, et cetera, et cetera, et cetera, for all the future cash flows, all the way up to Fn for cash flow n. So what types of projects does this fit? An awful lot. Mortgages, car loans, annuities due, which are really found most often in leases, and many other types of cash flow projects. So it's worth spending a little bit of time thinking about our discounted cash flow equation in this case, okay? Whenever all of our multiple cash flows are equal, we're going to be able to simplify our equation a little bit. So all of these cash flows are going to be equal. And if they're all equal, we can take them outside of the summation here, okay? So we're going to do that little jump here to bring it outside of the equation. Whoops, that's supposed to be the point of an arrow. It's pointing the wrong way, but you get the idea, okay? And that's nice because now we have just one number to solve for here, and using algebra we can solve for that one number pretty easily, okay? So there's a nice example here. I'm going to let you work out the details of this one on your own too. This is going to be for a 3-year mortgage, okay, and we're going to want to solve for the amount that the borrower is going to get in the beginning, CF0, or the way this cash flow diagram is shown, it's going to be the amount that the lender gives to the borrower, Mr. Small Net Worth, in return for these constant mortgage payments, $12,060, $12,060, $12,060. That's the way a mortgage works, is the you get a blob of money to help you purchase a home, and then in return you make a series of uniform payments to the mortgage lender who gave you the blob of money in the first place. Okay, so I think you can see pretty clearly here how to solve for this CF0. It's just like what we did before. You're going to have 3 pieces, add them up, etc., etc. Okay, so I will let you check my work on that and find that the amount loaned in this case in return for those 3 equal payments of $12,060 is $30,000, and this project has a 10% interest rate. Okay. And in general, good to make sure we can identify these cash flow diagrams for the borrower and for the lender. Okay, so for a borrower, you get a blob of money at t equals 0, which helps you buy the house. You use that money to buy the house. And in return, you have a contract that says you have to make a bunch of future equal payments. And from the lender's point of view, they put this blob of money into helping buy the house in return for the contractual payments from the customer. Okay, another example we could look at are car loans from Car Loan Company. And Car Loan Company has 2 types of borrowers. There are prime borrowers that pay 8% interest, and there are subprime borrowers that pay 10% interest. So the subprimes are more risky. They have more chance of getting fired from their job and not being able to repay the money or something like that. So the prime borrowers are going to be less risky. So clearly with your more risky borrowers, you want to charge them more interest because you're not going to be just making one loan, you're going to be making 100 loans. And 1 or 2 of these risky borrowers are going to flame out. So on a weighted average basis, considering the several flame outs you're going to have, you still want to be making something like 8%, which is what you get from your less risky borrowers who aren't generally flaming out. So that's why the riskier you are, the riskier cohort you're lending to, the higher interest rate that you want. Okay, so we're asking to find what's the annual payment per dollar of loan for each class of borrower. And again, I'm going to let you sort this through yourself. It's very clear. Again, it's also in the text. And what you should find, you should definitely verify this, please, that the prime borrowers who are paying 8% interest, the annual payment they have to pay per dollar of loan is 56 cents. And for the riskier borrowers at 10% interest, they have to pay back more. So that makes sense. If you're riskier, you have a higher interest rate, you got to pay back more. So again, you want to position yourself as a borrower as a very not risky borrower. So you get the lower interest rate and all of your financing gets cheaper. Okay. So a little bit more on risk, just to really hammer this home. Okay. In general, interest rates increase with a project's risk. This is true fundamentally because we find it to be true empirically everywhere. And what are some consequences of this? The US Treasury, remember, considered very, very low risk. It's our proxy for the lowest risk investment in the whole wide world. The US Treasury, therefore, can borrow money, in other words, issue its Treasury bonds at very low interest rates. Okay, in fact, the Treasury is considered so low risk that it's called, in quotes, risk-free investment. And risk-free is in quotes because there is inflation risk and there are some other risks, but the risk of the Treasury defaulting is virtually zero. Okay, and banks can offer the low rates on CDs because they're guaranteed by the Federal Deposit Insurance Corporation, which is essentially part of the Treasury. So that's how banks get such low rates on CDs. Subprime borrowers are going to pay higher interest rates to compensate for their higher probability that they will default. Okay. All right, and annuity project is just another example of a constant future cash flow project here. And again, I'm going to let you work through this one on your own. I think that you get the idea now, but I do want to focus with you on annuity due projects. Annuity due projects are annuity projects with payments made at the beginning of the period instead of the end of the period. So annuity is just like a mortgage, okay? Or standard constant cash flow project. Okay, it's just certain types of deals are annuities other than mortgages, but the structure of the cash flows is exactly the same. All right. An annuity due has payments made at the beginning of each period instead of the end. So mortgages, everything we've looked at so far, even before mortgages, payments are always made at the end of the period. We consider this end of period 0, end of period 1, end of period 2, end of period 3. So annuities due are going to be a little bit different. So why would you do this? Well, clearly the lender maybe wants their cash back quicker. What's very common, and this is true with leases, is that the borrower is paying upfront for the use of something during each period. Okay, that's really the key. So leases generally work like this, and we're about to see an example of how it works for a lease. Okay. So let's consider an example 3-year annuity due lease project. So we've got a lessor out there who's in the business of leasing 3D printers and other things. Okay, so she goes out and buys a 775 aluminum alloy 3D printer. I mean, that's pretty top end. This is about the strongest aluminum alloy you can get. And it's got about a 3-year life. So she goes out and buys one for 140,000 and change. And then the same day, just to keep things simple, she leases the printer to Green Car Company, GCC, just a company called GCC, short for Green Car Company. She leases it to them for 3 years via a 7% annuity due. Okay, that's what we'd say in finance. What she would say to Green Car Company is, I'm going to give you a 3-year, 7% lease. Okay, so good to know both sets of terminology. So we want to know, what is Green Car Company's annual payment? Okay, so first of all, this thing has a 3-year life. Okay, and she paid $140,400 for it. Okay, so she paid that today to the manufacturer. Okay, and she wants to recoup that money at 7% interest. She wants to make this investment in this machine grow at 7%. So what she says to Green Car Company is, later today, the same day that I bought the machine, you're going to give me a uniform payment, which gives you the right to the exclusive use of that machine for 1 year. And then at the end of the year, the beginning of year 2, you're going to give me another payment, equal payment, okay, just like the mortgage, equal payment, that's going to give you the right to use that machine exclusively for that whole year. And then at the end of year 2, beginning of year 3, you're going to give me a third and final equal payment, which gives you the exclusive right to use that machine for year 3. And then the useful life of the machine is over, it's dead, and we dispose of it properly somewhere. Okay, so that's the idea. So all you have to remember is to just keep your wits about you here, as you are discounting. Okay, so what we need here is to find out what this CF is, what this annual payment is. So let's see if we can do that. So clearly her present value, the total present value is $140,400. That's going to be equal to the uniform payment times what? We're going to have those, they've got to occur 3 times, okay? So times 1, that's going to be this one that doesn't get discounted at all, right? So that's the first one there. And then the second one gets discounted back by 1 plus R, 1 plus 7% to the 1, okay? And the third one gets discounted back by 1 over 1 plus 7% squared. So even though it's a 3-year contract, okay, the cash flows get discounted back by 2 years, 1 year, and 0 years. So this is a really nice deal for the lender. Okay, so she pays the $140,000 today, and then she's going to get her first payment back the same day from the folks that she leases this equipment to. So she recoups a bunch of her cost right away. All right, so we work this out. We have this equation here with only one unknown in it. What's our one unknown? The uniform cash flow. So I'll let you solve for that. And please do, you should always verify me, and you should find that the uniform payment is $50. So now we can put in our cash flow diagram here what these uniform payments are. 50, 50, 50. Okay, and they better add up. Good way to check our work. We have 50 discounted back to t equals 0, 50 at essentially t equals 0, brought back to t equals 0, still 50, so that's payment 1. 50 divided by 1 plus 7% interest to the 1 is 46.73. And this final payment, 50 divided by 1 plus 7% brought back 2 years, so that's squared, is equal to 43.67. I add them up and I get my 140.4. So that's great. So we find out that to make this deal work for our lessor, she's going to say to GCC, to Green Car Company, you have to make 3 equal payments of $50,000, one starting today, next one in a year, next one at the end of 2 years, beginning of the 3rd year, and that final one gives you exclusive right to use the machine for that next year. All right. Okay, I'm going to skip that page. And I am going to talk about perpetuities for a second. A perpetuity is just a uniform cash flow project with payments that stretch out forever to infinity. Okay, so how's that going to look for us mathematically? That's going to be our PV is we have our uniform cash flow outside of our summation sign here. So our PV is going to be equal to our uniform cash flow times the sum of 1 over 1 plus R to the TI, where I goes from 1 to infinity. So this is kind of a hassle to deal with, never good to have to keep summing out to infinity. It takes up too much time. So let's see if we can convert this to a closed form equation. I think we can just by doing a simple example here. So let's consider investing in a bank account that pays 10% annual interest forever. And so we'll put in $100 at t equals 0. Okay, so that's going to be our PV there. All right, that's our PV, our 100 there. And we get 10% interest. So at the end of 1 year, that 100 is going to grow to 110, but we take 10 out. So for the next year, what's going to happen? It's going to grow to 110 again, but we take 10 out, okay? And this describes perfectly a perpetuity. Our principal never grows or declines, okay? And it satisfies what? It satisfies that cash flow, which is 10, okay? 10 is equal to 10% times 100, or our uniform cash flow is equal to our interest rate times our present value. So we can find the present value of a perpetuity by simply solving that equation for PV. So the present value of a perpetuity, this is interesting, a string of cash flows that goes on forever, is equal to that uniform cash flow that we're going to be paid every year divided by the interest rate. And that's really the truth, the whole truth, and nothing but the truth. So we've gone from a series that goes to infinity to a nice, easy to remember closed form equation. This is probably a good one to remember. It comes up in finance fairly often. Okay, growing perpetuity we're going to skip. It does come up in advanced finance here and there, so you can refer back to this and the pros in the text if you ever need to, but I'm going to skip it for now. Okay. I want to talk about now future values of multiple cash flow projects. So sometimes we want to know if we have a cash flow coming in a year and a cash flow coming in 2 years and then a cash flow coming in 4 years, what are those all going to be worth in 6 years if we put them in an interest-bearing checking account or something like that? So I'm gonna jump right to this example to talk about this. So let's say, what's the future value of cash flow one, meaning comes at, we get this, get at t equal 1, okay, if it's invested at 6% until t equal 4. So we're not getting it now, we're getting it at t equal 1, but it's going to grow till t equal 4. So that means it's going to grow for 4 minus 1 or 3 years at 6%. So I think I can figure this out. The future value at time 4 is going to be what we get there at time 1 times 1 plus 6% to how many years? How much time does it have to grow? 4 minus 1 or 3 years. And that works out to be 119.4. Okay, so that's the general idea, okay? And we could do this for a 3 cash flow project, and I've got some algebra here showing you how it works, and I do work my way down here to a nice formula, but I think honestly you should just think about this example and use your common sense, and you can get there just fine. So let's do that with a multiple cash flow future value example. So let's consider USEC. USEC has gone bankrupt, and you'll see why in a minute. But before it went bankrupt, it used electrical energy for its gaseous diffusion uranium enrichment plant. And one of the reasons they went bankrupt is that gaseous diffusion uses 50 times as much energy as centrifuge plants, which is today's state-of-the-art technology. So that's not good. So basically, within about the past 10 years, anyone who was using gaseous diffusion has been put out of business by more efficient plants that use centrifuges. So at the time, however, before they went bankrupt, they knew there were these clouds on the horizon, so they wanted to lock in energy prices, and they agreed to pay the TVA. USEC was down in Tennessee. They agreed to pay the Tennessee Valley Authority $89 million in 3 years for 1,000 megawatts of power to be delivered in year 4. Okay, so this is what's called a forward contract. Okay, and how is USEC going to work this out? They want to put some money aside now to make sure that they're going to have enough to pay the TVA when the time comes. So they look around and they find that their bank is offering them a guaranteed 9% interest rate in money market accounts for the next 3 years. Okay, so USEC comes to us, God help us, and they ask us, will 25 million set aside at the end of each year for 3 years grow to 89 million or more by end of year 3? And if not, what alternatives would we recommend? Okay, so let's just look at a cash flow diagram for this. And so I think this is actually very helpful. Okay, so the CFO is saying here we are at, as usual, at t equal 0, okay, and the CFO is saying to us, I'm proposing we put in 25 into this 9% interest-bearing account in a year, do it again in 2 years, do it again at the end of 3 years, a day before we give the money to the TVA, and is that going to be enough? And you can see either by futzing around with our formula, which is fine if you want to do that, and it's really good if you're programming in Python or C++ or something like that. But for small problems like this, we can just suss it out with a cash flow diagram to answer this question. So how do we do it? We say to ourselves, we say, well, self, This 25,000 is going to grow at 9% for how much? 1 year, 2 years. So I'm just going to take 25 times 1.09 squared, and that's going to grow to 29.7. Okay, then the second payment we're going to put in 2 years from now. That only has 1 year to grow. So what's it going to grow to? 25 times 1.09 to the 1, or 27.5. And then the third amount we're going to put in 1 day before we write the check to the TVA, going to be 25,000. I add these three up and I get 81.95 thousand, which is less than 89. So this clearly does not work. Okay, so we're going to have to do something else. So we tell the boss that this does not work. Okay. All right. And so let's see if we could think of some alternatives. Clearly, we could try to find a higher interest-bearing account, but 9% is pretty high. Let's say that doesn't work. How about this for some creative out-of-the-box thinking? How about if we say to the CFO, this is fine, and we understand you can only afford to put in 25 million a year right now, because times are tough and we might be going bankrupt. But how about instead of waiting for a year for the first payment, can we cough up 25 million right now? So we'll make our first payment now, another one in a year, our second one in 2 years. If we do that, the advantage of doing that is this first one is going to grow for how much? 1, 2, 3 years. So we take 25 times 1.09 to the 3, it'll grow to 32.38. The payment we would make into the interest-bearing account at end of year 1 is still going to grow for 2 years and grow to 29.7. And the payment we make at end of year 2, which would now be our final payment, is going to grow for 1 year to 27.25. And we get 89.33 million. So that's pretty good. We only need 89 million. This is greater than 89 million, so this works. Okay, so what I think it would be fair to you to do would be to suggest for this brilliant idea that you get paid a bonus of 33,000, right? Which is the extra amount. Okay, so that might be a good suggestion for you to give to the CFO after you come up with this brilliant idea. Of course, you might get fired for that suggestion too, so it's a little risky, but you might want to think about it. Okay. And now I'm going to take another short break and we will come back and start talking about compounding periods.